So, with the global warming and uh, the government of India, right, in the Paris Convention, committed that we have to go green and we have to be carbon neutral. So, with that, right, and with that, the import of fuel, right. So, we have been, initiated. The government of India initiated this faster adaptation and manufacturing of hybrid electric vehicle, which with the focus of holistic growth of electric vehicle industry and create the job in India. So number of cars per thousand people in developed countries, like you can think, for every 1,000 people in America, right, there are 837 cars, and the average in the world, right, it is 156. Now imagine, like in our country, like how much the per thousand people, the car population, it is only 22. You know, so you can see that we have very few car, like powered by fossil fuel. Okay, so the thing is, because we have very few car now, what are the car is going to be added? So it is better to be electric powered, so that we don't pollute much. So basically, vehicular pollution is one of the you know biggest contributor, and like it contributes more than 56% of a CO2 emission in India. So the thing is, the target is to address that. So for that matter, the government of India, right, had mandated that all the car manufactured and sold in India, should be electric car by 2023, and the Germany also promised the same. So this is I'll cover this topic: Niti Aayog report and NEMP, National Electric Mobility Mission Plan, FAME India scheme, and what is its objective, developing EV policy and who are the stakeholders, and the phase 2 of India, the FAME scheme. Like after FAME, right, the phase 2 has been introduced, and the most important thing is the phase manufacturing program. Okay, so that is what is also very important. So which will create the job in India. So battery market potential in India and electric bus market, like how it is going. So I'll just quickly run through. Basically, Niti Aayog report, it says that electric cars and buses and metros could help India to save, $60 billion in 2030. So basically, we import, a lot of oil, so that makes, and one of the critical thing is if, if we shift to the electric mobility, then 64% of the energy demand, it can be saved. Basically, like what we call is shared electric mobility. So these days, like you'll be seeing all the metro cities and the satellite, towns, right, bigger, cities and towns, right. One of the most popular mode of transportations, like they're promoting is the metros, metro trains. So that is what is, and in India right now, all the the train services has been converted into the electric. Now we don't have any more like in earlier days the coal based locomotive engines driving the trains, and then the diesel engines, and those things are now the past. So all the things are by electricity. So the thing is, these are all used by the public. So all the public transports, all the local trains, metros, electric buses running in and around the cities, then the taxis, like, which are shared, not individual, commuting. So with that kind of focus, this much of energy can be saved. So subsequent drop in the petrol and diesel consumptions would be 110 56 million tons of oil equivalent, or 1.8 terawatt hour energy, enough to power 1,796 million homes in the country. So, like we can save a 3.9 lakh crore in 2030. The Niti Aayog chairman, right? So he is, very focused on, driving on this. So what is the National Electric Mobility Mission Plan, and what is its objective? So National Electric Mobility Mission Plan was unveiled on 9th January 2013, and its objective is to enhance the national energy security and mitigate adverse environment impact, boost domestic manufacturing capabilities for electric vehicles, and create the jobs. So the scheme has 4 focus areas. The first initial is the technology development, demand creation, pilot projects, and charging infrastructures. So the government has really planned very well in India for national electric mobility mission plan, and it gave the National Electric Mobility Mission Plan. The objective has given rise to the FAME India scheme. FAME is nothing but faster adaptation and manufacturing of hybrid and electric vehicles. So the target of NEMP was 6 to 7 million hybrid electric vehicles sold in 2020. So we are far behind than this number. 2020 is almost done. Another 3 years, right? 2020 will be over. With this COVID situation, so we lost almost 1 year. But if you know that one of our vehicle like Nexon EV is selling very good, but we are far behind. But this 6 to 7 million, right? It covers not only the 4-wheelers, it covers 2-wheelers, 3-wheelers, on all aspect of it. So it's a Government of India initiative scheme. So it is not supporting any particular segment of the people or populations. It is for everyone. So 2-wheelers, scooters, electric scooters, everybody is covered in this scheme. So 9,500 million liters of estimated cumulative fuel savings, and 2 million tons reductions in the pollution and greenhouse gas emissions. 65,000 direct and to 3 lakh indirect job creations. Okay, basically 3 lakh people will be supporting the development, the component manufacturing, and in the directly industry, right, who will be making, basically the OEM will be making the vehicles, 65,000 people, so these are the kind of things are. So FAME India scheme is the pilot initiative for the first 2 years under the MMP approved by the Finance Minister, notified on 25th March 2015. So there is a clear objective of the FAME is to promote manufacturing of electric and hybrid vehicles technology, ensure sustainable growth of electric and hybrid vehicle technology. Department of Heavy Industry is implementing FAME India scheme in phase 1 from 1st of April 2015. Total outlay, right? How much money the government is going to give in the subsidy in the FAME India scheme? First, like it was 795 crore and to 895 crore. And the scheme was initially up to 31st of April 2017 and was extended up to 31st of March 2019. So initially, the phase 1, the objective was for the demand creation, meaning the people should start buying it. Now, if the people buy it, if they don't have any charging infrastructures, right, where to charge it. So the FAME 1 scheme, right, the way it wanted to be, right, it didn't progress that far. So the phase 2 scheme was proposed to give a push to the electric vehicles in public transports, focusing for bigger subsidies, in which the people uses, so the common people uses, like the electric buses. So seeks to encourage adaptation of electric vehicles by way of market creation and demand aggregations. The draft scheme envisages the holistic growth of EV industry. So the draft two, right, the PM2 scheme, which has a total outlay of 10,000 crore, right? So and it's for the period for 3 years from 1st April 2019 to 2022. So in a bigger scheme, so this has been defined in a much better way, supporting for the infrastructures, R&Ds, everyone. So the allocations for the scheme for the 2019-20, it is estimated to be 1,500 crore and 5,000 crore for 2020-2021 and so on. So this is quite interesting, like how developing the EV India policy in 2013, the National Electric Mobility Mission Plan was unveiled, and in 2015, the FAME India scheme came up. Then slowly, like all the state government, they have come up with their own policies to support the electric mobility mission plan. So in 2017, the Karnataka EV policy came up, and then the Telangana draft EV policy came up. Then in 2018, there's a major push, like Maharashtra EV policy was framed. Then UP, Uttar Pradesh draft EV policy, Kerala, Uttarakhand, Delhi draft EV policies. So then the clarification on the requirement of the license to operate EV charging stations by Ministry of Power, it was clarified. So people, those who want to set up a charging stations, guidelines and standards for setting up public charging infrastructure by the Ministry of Power. Then in 2019, the amendment in the model building bylaws by Ministry of Urban Development. So the Ministry of Urban Development, like they also came up with the rules and regulations, and it said that the new housing societies, they have to create a charging infrastructure facilities for the electric vehicles. Otherwise, the housing societies, like it will not be given permissions. Something of that sort. You can think like that. So, Ministry of Urban Development, they came up with their own policies and bylaws, and PMP, like which is nothing but is the phased manufacturing plan for EVs and its components. What happens is, because of the demand creations earlier now, like in 2015 onwards, right, people started importing the EV component kits, from mainly China. So they started fitting into the vehicle, so and started selling as electric vehicles. So that's the kind of thing is, but the government has tightened it. They told, define which components of the electric vehicle has to be localized, locally manufactured, to be used in the vehicle to get and meet the FAME2 scheme. So if the components are not manufactured in India, like the people in India, the job is not created, So that's the one of the biggest thing. So there are many stakeholders for implementing the EV policies. So it is under the aegis of Department of Heavy Industries, like they are the framer and creeper of they are the like defining the policies, like what is FAME 1 and FAME 2. The Niti Aayog is the guiding, like national mission on transformative mobility and battery storage. So they are supporting in the kind of guidance, and so Ministry of Power clarifications on the requirement of license to operate EV charging stations. So like they know the power grid capacity, like how much, so they are framing. So basically, like in the night, if all the vehicle electric vehicle goes for charging, right, the grid may so everybody have to play, right. The Ministry of Road and Highways Transport, green license plate for electric vehicles. So you have seen on the road, right. So the electric vehicle which is flying, like if you see a number plate, right, which is green and white text, so it is electric vehicle. So all those rules and the regulations are formed by Ministry of Road Transports and Highways, Ministry of Urban Development. I told you, like you know amendments in model building bylaws, setting up charging infrastructures in the new housing societies which will be coming up. Auto mission for rejuvenation and urban transformation. So which is Amrut specializations in the urban buses. So the guidelines, like how the electric buses will be flying. So here, like you are seeing, everywhere, like there are many stakeholders for implementing the FAME scheme, and all the stakeholders, they have to work in close sync to make the FAME implemented successfully. So phase 2 of the FAME India scheme, what it says is FAME2 scheme is proposed to be implemented over a period of 3 years with effect from 1st of April 2019. So the FAME scheme, like what it is demand incentives, like whatever the committed expenditures of phase 1 which was not used, like to continue to give subsidy for that. Further, give some demand incentives for the vehicle, set up a clear guidelines and infrastructures and subsidy for setting up charging stations, like what we call is the charging infrastructures, and administrations of schemes including the publicity. So for that also, right, educating people, like so for that also, like the uh, the money is earmarked, right, the budgets. So demand incentive, like for 2019 and 20, like 822 crore. 2020-21 is 4,500. Like, so every year, right? Like the things are earmarked. Like how much budget is. So the total outlay for the PM2 scheme, you can see, is 10,000 crore here. So key message: the demand, incentives will be based on the battery capacity. So that is how much kilowatt hour of the battery pack is installed into the vehicle. So there's a limit for that also. And the FAME2 scheme will be applicable mainly to the vehicles used for the public transport or those registered for commercial purposes in 3-wheeler and 4-wheeler and buses segment. However, privately owned registered 2-wheelers will also be covered under the scheme, under the scheme as the mass segment. So quantum of the demand incentives, like in order to rationalize the demand incentive across the vehicle segments and different technologies, the project's implementation and the sanctioning committee has proposed to extend the uniform demand incentives of 10,000 rupees per kilowatt hour for all vehicles. So basically, like if you buy a electric scooter, like that has a 5 kilowatt hour battery pack, right? So probably like you'll get 50,000 rupees as a kind of subsidy. And for the buses, the initial uniform maximum demand incentive applicable is 20,000 rupees. So for the buses, it is 20,000 rupees. It is more basically buses are used mainly by the publics. So the subsidy is more there. So demand incentives for electric buses will be provided only on the operational model and will be delivered through the state and city transport undertakings. So like the based or our PMPL, right? So it is executed through them. And nowadays, like what is happening is the model has changed to the OPEX model. Basically, the OEM will be owning the bus. They'll be in charge of maintaining the buses, and they will be paid based on the kilometers the bus has run. So that's the kind of model. So in order to restrict the high-end vehicles from availing government-funded demand incentives, the committee has proposed to restrict the incentives of the vehicles on the basis of the ex-factory prices less than a particular threshold value. Now somebody buy a Tesla, which is 50 lakhs or something, and he says that give me subsidy, like it has 100 kilowatt hour battery packs or 10 lakh subsidy. So that kind of thing is not done. Okay. So the maximum incentives per vehicle has been capped at certain percentage of the cost of vehicle, which will be subject to review and revision committee. To begin with, the cap on the incentives of the buses will be 40%, the cost of the vehicle for all categories, and it will be 20%. So this cap is provided here. So the maximum subsidy one can get is 40% for the buses and 20% of the all other vehicles. So for charging infrastructures, the scheme envisages support for setting up the public charging infrastructures. All the charging stations will be established as per the guidelines issued by the Ministry of the Power. And as far as charging of electric buses are concerned, the committee has proposed to provide to buyer one slow charger per e-bus and one fast charger for every 10 buses to be funded under the scheme. So basically, slow charger and the fast charger, meaning the slow charger, basically, like you can think of the charging can happen overnight, and fast charging, right, it can charge the bus for say 2 hours, or at max 1 hour, and at still as of today, right, 1 hour charging is not so not happening, so it is 2 hours, you can think. So for every 10 buses, the charging, for charging, one fast charger is covered under this subsidy. So with respect to providing a funding on the establishment of the charging infrastructures, it can go up 100% of the cost depending upon the project proposal. So if the proposal, based on the project proposals, the government is ready to fund 100% of the charging infrastructures going to be set up. The project for charging infrastructure will also include infrastructure projects like pantograph charging, flash charging, etc. So there are many charging possibilities. So those also will be covered. DHI will be responsible for overall implementation of the scheme and removing any obstacles if arises during implementations. So DHI, they are the basically owning the implementation of the FEM. So they will be responsible for clearing all the proposals and everything, and they'll be supporting and helping the permissions from all other agencies. So project sanctions under FAME2 scheme will continue in operation as per the terms and conditions issued during the time of the sanction. And for creating consumer awareness and promotion of the scheme, suitable program will be conducted by DHI industry associations, volunteer organizations, through education and training, organization of the business meets, seminars, conferences, etc. And for that, the budget also has been earmarked. So this is quite important slide. So you can see here the vehicle segment wise incentive, maximum number of vehicles to be supported. Say for under FAME2 scheme, registered e-two-wheeler. So maximum 10 lakh vehicle will be supported. Maximum battery size, maximum 2 kilowatt hour. For 2 kilowatt hour only, like the vehicle may have 3, 4, 5 kilowatt hour battery pack, but the subsidy is only for 2 kilowatt hour it will be considered. So 20,000 rupees subsidy will be provided. So maximum expected prices also is capped here. It should be 1.5 lakh rupees. So for 3-wheelers, like the battery capacity will be 5 kilowatt hour and is for 5 lakh 3-wheelers, and the subsidy will be 50,000 rupees, and the vehicle cost capped at 5 lakh rupees. So for 4-wheelers, 35,000 4-wheelers will be under this scheme for subsidy. The battery For 15 kilowatt hour, like although your vehicle may have 30 kilowatt hour battery pack, but you will get a subsidy for 15 kilowatt hour, so it is 1,50,000 rupees subsidy will be awarded, and the vehicle cost capped at 15 lakh rupees. And for the strong hybrid also, right, which has electric propulsion as well as the gasoline engine propulsion, for that 20,000 vehicles, and like the battery kilowatt hour is 1.3 kilowatt hour and 13,000 rupees subsidy. So which is not really very lucrative, that way, like 13,000 rupees subsidies, and for the vehicle cost for the strong hybrid, right, because you have to have electric powertrain as well as a gasoline powertrain. Now that makes it expensive. So and with some 13,000, so this proposal doesn't really very lucrative. So all the focus is on the electrifications, electric propulsion. And for the electric buses, 7,900 buses, 7,090 buses, and the battery kilowatt hour is capped at 250 kilowatt hour. So that is, total incentive will be something like 50 lakh rupees. So for every electric buses, you get a subsidy of 50 lakh rupees, and the bus value is capped at 2 crore. So that is how, like it looks like here. So here, if you look, all the maximum share of the subsidy is taken by the electric buses, because it is, for use for the publics. Now here, like, is the phased manufacturing scheme. Like initially, like government agreed to allow CBU, a completely built unit, like the buses and trucks, to be imported, and the basic customs duty until 30th of January 2019 is 25%, and it is proposed to increase to 50%. Basically, the duty is increasing, so people will think of manufacturing in India, so that's what is the focus is. And SKD is the semi knockdown, so it was imported, then it was 15%. Then for PV two-wheeler buses and trucks, right? So for semi knockdown also, like proposed BCD from April 2020 onwards, right? So it has to be, like it is increased like 10%, 25%, 25%. So, and completely knockdown kit, like the customs duty was 10%. So still lesser on this. Basically, if you bring the completely knockdown kit, so you need more people to engage to assemble the vehicle and sell, right? So for that, the basic customs duty is proposed to only 15% from April 2020 onwards. And the thing is, for the lithium-ion cells, right? People in India, so far as now, lithium-ion cells are not really, manufactured in a commercial scale. So it is 5%, and it is proposed to 10% from April 2021 onwards. So they had given a more time, but because of this COVID situation, like which almost 1 year is gone, so probably they'll extend, government will extend this timeline. And parts for use for the manufacturing of the EVs, like the components, so that didn't had any taxes until customs duty until 30th of January 2019. But it is proposed to increase to 15%, from April 2021 onwards. So here, right, different components like code, right, from 1st April 2021, AA plus, so an effective date of indigenization of the parts, right? So from when, so different categories of the parts, right, say wheel rim and all, right? So somebody should not really import wheel rim, right? So power and control wiring harness, so it should be localized in India. So all different vehicle classes like MCB circuit breakers, electric safety devices. So when it's to be for which category of the vehicle, So government have clearly defined. No, so people have to really localize all those components. So here, I know, like is a survey report. Is published by CES, like the cumulative the battery demand in India from 2018 to 2025. So you can see the total battery demand is something like 122 gigawatt hour, right? So that's what is it is increasing exponentially, right? Whatever the demand it was. So two-wheeler, so mainly like you can see here, four-wheelers and the buses. That's four-wheeler, three-wheelers and the buses. They'll be topping, and two-wheelers also, right? Almost getting good chunk of shares of the demand. So that's how the thing is. And here, I'm just trying to show the battery market for electric buses in 2018. So this is what is a bit, couple of years old, So leading battery cell suppliers in India for EVs. So Samsung SDI, then BYD, like they use LFP cells. Samsung, they are supplying NMC cells. LG Chemical, they are supplying NMC cells. Leclanc is MG Chemical cells. There is a Calb is LFP, and Cattle CATL is LFP cells. And the leading battery pack integrators, in India, like Octaland Power Systems, Sun Mobility, KPIT, and BYD. And the share of like LFP in India, like it is more than because LFP is known to be very safe cell compared to all others, So, but NMC is also quite popular. So, the buses, some buses are using Samsung NMC cells. So that is how is the split look like here. And LMO is not really very popular, in terms of the safety of the cells. So Tata Motor is like one of the leading in the buses. Tata Motor owns 6 tenders for the 10. Are you able to hear me? Hello.
Yes, sir.
Okay,
You're
great.
audible.
Yeah. So Tata Motors owns 6 tenders out of the 10 tenders floated by the different STU state transport units under the FAME India scheme in 2018. So out of these 6 tenders, 5 tenders were on the capex model. So capex model meaning like the operator, right? They buy the buses, and they own the bus. And in the opex model, like the OEM, right? The Tata Motor will you know owning the buses and running the buses, and will be charging on the per kilometer basis. So they'll supply 255 buses to the different cities such as Kolkata, Indore, Lucknow, Jaipur, Guwahati, and Jammu. And as per Tata Motors, the first batches of the buses already delivered. This is already done. This is quite old. Then the other companies like who are supplying the buses are Electra, also Cleland. Then there's a Photon PMI, and ICER has joined hands with KPIT, and they are supporting buses. So that's what is in brief. So that's what is my last slide. So thank you so much. And if you have any questions to me, you can ask me, or like I'll go to my next section on the battery thermal management.
So participants, are there any questions? So we can take the questions in the last after the second presentation also, sir. So you can continue with your second presentation.
Okay, great.
Okay.
Uh, I'll continue with the next topic is introduction of the thermal management of XEVs. XEVs, represents the electric vehicle as well as the hybrid vehicle. So because it is, So that's what people represented it XEVs, to make sure that it is covering both hybrid and electric vehicles. So, but I'll be covering in this session only for the battery part of it. Okay, for the lack of time. So that contents will be like I'll be talking on the type of electric vehicles, the thermal management of the batteries, how do the lithium-ion battery work, importance of the temperature in the battery, and how is the heat generation process, and lithium-ion battery failures, how the battery fails, battery cooling methods, need of battery thermal management systems. So I'll be covering until here. I'll continue so type of battery electric vehicles. Basically the electric vehicles, hybrid electric vehicles, or plug-in electric vehicles and fuel cell electric vehicles, all these are the different classified of the vehicles, and based on the source of their power, right, the vehicles are classified. And basically what happened is in these vehicles, a battery, everybody uses a battery for sure. So even for the fuel cell electric vehicle, where the main power source is from the fuel cell reactor, but the fuel cell reactor, right, it directly cannot give that required kind of power. So there is a buffer in between which is used. That's what is nothing but is the battery pack. But the battery pack capacity need not be a very big one, because almost all the energy will be provided by the fuel cell reactor. So basically for longer range of the fuel cell electric vehicle, one need to carry a bigger a hydrogen cylinder on top. So the amount of hydrogen cylinder, how many kgs hydrogen it will be carried. And for the BEV, which is a pure battery electric vehicle, for which one need to have a bigger battery pack, meaning more kilowatt hour, to have the bigger range of the vehicle. And for hybrid electric vehicle, basically which will not really have a bigger battery pack, but PHEV battery pack, which is a kind of have a drive range, for electric drive range, for which if somebody want to have more drive range than one electric drive range, then he need to put more battery pack kilowatt hour in the PHEV battery pack. So this is a battery electric vehicle in which I just explained for this, but all others then I can skip. So here we have a motor, we have but power electronics controller, DC-DC converter. DC-DC converter is needed. Basically, we don't have the alternator, or we don't have the engine to run the alternator. So we have a bigger battery pack, which is 350 volt, and for all the auxiliary powers like the horns, the all other the lighting systems, the music systems, they need 12 volt supply. So 350 volts to 12 volt, so there's a DC-DC converter. And here you are all from the electrical department, so I'll be a fool to speak up electricals to you, because you are already knowing all of these things. So thermal system, for cooling the battery pack and the motor, of course we'll need to have a thermal systems, and auxiliary battery, 12 volt battery is a must. Onboard charger, basically we need to charge the battery pack. So fast charger are available outside, but for every places we might not have a fast charger, so we have to provide an onboard charger, so which may be 3.3 kilowatt hour charger or 6.6 kilowatt hour charger, based on the battery pack size. Then we have the transmission, which is nothing but is a transaxle, having a single speed gearbox, and the charging port for charging the vehicle, and traction battery, of course. So in the pure electric vehicle, we don't have IC engine, and only electrical drivetrain we have, and the battery pack is very, very large, from 20 to 100 kilowatt hour, or whatever people would like to pack in for their desired range. And this is what is the hybrid. So has IC engine and electric motor, and the battery get charged by the engine, and battery pack size can vary from 1 to 12 kilowatt hour. And for the PHEV, like it has the same IC engine and electric motor. The battery get charged by the engine and can be charged from the external sources. The battery pack can be large or medium size to have the desired range of the vehicle. And here is the fuel cell vehicle. Like here we don't have the engine, but we have the fuel cell, and we have the hydrogen tank. So I'll just skip these slides, like series, parallel, hybrids. The focus is not all those in these sections. So like what is but if you want to know something like what is a P0, P1, P2, P3, and P4, P5 hybrid, I'll just take you through. So in the P0 hybrid, instead of alternator, like a BHG is a belt starter generator which is used, and P1 is a starter generator on the crankshaft, and for P2 is a downstream of disconnection on the clutch. So, and for P3 is after the gearbox, like the location here you are seeing it. P2 is like this is the engine, and this is the gearbox. So in between, like P2 machine is placed, and P3 is after the gearbox. Then P4 is on the rear axle, and P5 is on the wheel. So this is what is the location. Based on the location, people call it P0, P1, P2 hybrid. So like our topic starts from here: thermal challenges within the powertrain electrifications, the cooling and heating of traction of the battery pack. So traction battery pack is important, like which is driving the vehicle, which is nothing but is a kind of engine replica for the electric vehicle. So it is the source of all power. So that's what is the battery pack. So as an engine, like you have a active cooling system. So for the battery pack also, we have to have active cooling systems, and like we'll take a deep look in it, how it works. The cooling of traction motor and the power electronics components, motor controller, DC-DC converter, onboard charger. So once those are used, so they also emits heat. So those heat also you have to remove. And the passenger compartment, of course, for the climate control, right, AC, like we have to remove heat from the passenger compartment, and optimizing efficiency with the target of reduced energy consumptions and increase the driving range. So as much as we can optimize the cooling requirement. So basically in the electric vehicle, the source of energy is the battery pack. So most of the energy one should use to maximize the range, but not to drive the water pump, coolant pump, or the AC compressor to cool the cabin and all the components which are generating the heats. So it is very, very important. So the thermal simulations and CFDs is very, 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 very critical, and to optimize the size of the battery thermal management systems, so that we can get the maximum driving range. And we have to like automate the climate specific strategies. So based on the climatic conditions, we should try to optimize the on the battery the cooling systems. So important of lithium-ion batteries in the EVs. So battery is the critical component in EV and HEV. So it enables hybridizations and electrifications. It provides power to the motor for accelerations and provides energy for electric range and other auxiliaries. Helps in downsizing and eliminating of the engine and enables recovery of waste heat. Basically, like we have the recuperations, like when the vehicle is decelerating, like the motor becomes a generator, so that energy which it is producing, right, that is dumped into the battery pack. So saves fuel and reduces emissions. So our objective is that only. So now thermal management systems in the batteries, right? So it will add cost, and it will add weight, and it will need a place, as a volume space to add it into the vehicle. So the vehicle, is maximum vehicle and space should be used to accommodate people, but if that is what is the thing is, then like if we reserve all the place in the vehicle for people to sit, and there's no place for the battery thermal management to accommodate, the vehicle cannot be made itself, right? So we have to look from all aspect of it, and we have to balance it out. So it is a added cost, but it is a necessity evil. So without the battery thermal management systems, like you cannot make a vehicle, and you cannot uh, do any design of the vehicle itself. So could decrease the reliability and the durability. Basically, like we are adding in the components, so that will cause more failure risk. So it will add reliability and durability, but it is needed. So we have to add it, no matter what. So decrease the performance with aging. Of course, anybody like which will be becoming old, right, performance will certainly be reducing. Raises safety concerns. So once like you are coordinating in adding failure risk, of course the safety concern also will be raised, but we have to add in the system for sure. So this is just to explain like how the lithium-ion battery works. Like here in the lithium-ion battery, right, we have a anode, cathode, separator, and electrolyte. So on the right hand side, if you look, the open sections of the battery, right, which is a copper coated with graphite, okay, and which is cathode. So what happens is, and the copper is for current collector, and there is a separator, like which is separating the anode and the cathode, and there's aluminum anode, and there's a electrolyte in between, which is enabling the transportation of ions from anode to the cathode, and this aluminum foil which is used for the current collector. So these are all like if you see is very very thin, so all are put together. So all these, right, the electron flows from anode to cathode, and the ion also flows through the separator, from anode to the cathode. So that's how is the basic mechanism of cell working. The cathode and the anode determines the basic performance of the battery. The electrolyte and the separator determines the safety of the battery. So the electrolyte and So everybody has its own function, right? So it has to do its job. So function of separator is to ensure that the anode and cathode is not short circuited. So the gap is maintained. Also, like it has to allow the ions to move through you know so to and fro. And the electrolyte, which is nothing but is a lithium ion salt, dissolved in uh, organic solution. So that enables the movement of the ion. So here, right, current collector, which is aluminum, and in the positive electrode, right, cathode, you have the active material coated with a mix of graphite binder. So the active material, it can be LFP, LMO, or LCO, or NMC. And the electrolyte, it can be LiPF6, lithium ferrophosphate salt, or there's other lithium, boron, fluorine, then SO3 CF3, salt dissolved in ethylene carbonate. you know then the separator is nothing but is a polyethylene, like just, which is kind of, you can see, is a plastic sheet, polyethylene. But this polyethylene, or polypropylene, these sheets are very porous, so making sure the ion movement happens. And the separator like allows the ion movement. And the negative electrode, which is anode, made of graphite. And the binder, it is uh, coated onto the aluminum foil. And negative current collector is copper. Okay, so negative and binder, like what is is polyphenol dinofluoride, PVDF. And SBR, like, which is nothing but is a styrene butadiene rubber. So that's how the thing, is the constructions. And this is how the flow of you know during the charging and the discharging. Now during the charging, like the ions are coming back to the anode, and the electrons are coming, so you're forcing the electrons to come back. In the battery, right here, in the previous slide, like here, you know we are not talk of yet the solid light interface, SCI layer. So what is SCI layer? Is solid electrolyte interface. Like what happens is, between anode and cathode, right, the separator and the electrolyte, which is there, right, in normal conditions, like operations, right, when the battery is charged for the very first time, right, a very thin layer, the passivating layer is formed, so which is called the ACI layer. This ACI layer is essential for the stability of the lithium ion cells, using carbon anodes. So what happened is, this makes a small barrier, so that the anode, like from cathode, the ions, right, cannot freely come to anode, and get discharged of the cells. So for that, that small, very thin, passivating layer is formed. So this thickness of the ACI layer is not homogeneous and increases with the cell age, and increasing the cell internal impedance, and it reduces its capacity and its cycle life. So this is ACI layer. It's a necessity evil. So we need it, but too much of it, like it reduces the cell capacity and the cycle life. The ACI layer increases the cell internal impedance and reduces the possible charge rates, as well as the high and low temperature performance. So it is needed in the lithium ion battery, but with the edges is formations, and uh, it becomes, the layer becomes thicker, and and it has uh, it has to be there, kind of thing. So I hope you have got the importance and requirement of this ACI layer formation. Like solid electrolyte interface. So under a potential requirement charge discharge, right, this barrier get broken for the ion transport to move. If this layer is not there, then in a normal storage condition, the ion from cathode will be traveling to the anode, and the battery cell will be getting self discharge. So to prevent that, this ACI layer is important to have it. So this shows different form factors and of the cell, the cylindricals, and the flat jelly roll, like, which is a prismatic cell, and the pouch cell is made by stacking, like anode cathode separator is stacked one over each other, and it is put in a aluminium and polythene layered plastic casing, so that's what is it's called a pouch cell. It's like it's a pouch. And after that, the electrolyte is filled in, vacuum, then electrolyte is filled in, all the air is removed. So that's how the things are done here. So what I'm saying is, like, the different cell format poses different challenges in the manufacturing of the battery pack and the thermal management, like the removing of the heat. So the cells which are put together to make a module, and a lot of modules are put together to make a battery pack. So importance of the temperature. So here, like what we are showing is uh, the discharge curve of a 20H lithium ion cell at very lowest temperature. So here, right, you'll find that at 45 degrees centigrade, right, ambient condition, right, the cell is operating at 3.5 volt, and you are able to get 20 ampere hour current. So 20 ampere current you can draw for 1 hour, so that's how is the capacity defined. So in this, like what we are seeing is, at a higher temperature, like like I can get a high voltage, and I can get more capacity. But at a lower temperature, say minus 30 degrees centigrade, the cell, right, I can get say 2.5 volt, and I can get half of the capacity, like 10H. So that is how, like, as and when the temperature increases, like the cell capacity increases. But are we able to operate the cell at 45 degrees centigrade? Then if you're operating the cell at a high temperature, then of course, like, we are overstretching, stressing the cell. So how that is good or bad for the cell to use, so we'll look into all the aspects in the subsequent presentation. So we are continuing with the importance of the temperature, like ambient operating conditions. Temperature, like how it happens is, like, so here we are doing a constant like current charge discharge, 3 to 4.2 volt at 25 degrees centigrade. So the demand, right, C rate, what we call the C rate, like, so I'll just go back to the previous slide here. So here, like I'm just drawing 20 ampere hour, 20 ampere for 1 hour. So that is what is 1 C rate. So if we draw 40 and ampere, right, then it will be 2C rate. Then I can draw it for only 30 minutes, So that's how is defined, like just to explain the C rate. So if you want to draw more current, like 1C, meaning whatever is the nominal current you can draw, right? You are drawing that. So the capacity per H, right? So that's how you are, so more the current you want to draw, right? 18C here, right? Your capacity like per H of the cell, right? You'll be, reducing. Okay. So battery life, right? So what happens is, like, when you leave the battery pack, right? So with a, with the time and the temperature and at what state of charge, right? At how much charge in the battery cell it is stored, right? So that will, depend the calendar life of the battery pack, the time, temperature, and the state of charge. So, like how long, like this, what is the, shelf life of the battery, like it will depend on the time, for how long it is stored, although like in lithium ion batteries, the self discharge is very low, but it does discharge, right? So if you, store say 20 H capacity cell over 2 years, right? It will be, 19.5 H. You'll not get 20 H after 1 year, So with time, the aging happens. So at the elevated temperature, if you store, right, so the aging will happen at a faster rate. So the batteries are, advised to operate and store at, 25 degrees centigrade. So I'll just come back to those slides, like you'll find it that then the state of charge, right? If you store, like the cells at a higher state of charge, like if you charge the battery cell fully and if you keep it, right, so it has more energy, so it will be have a prone to discharge. So, ideally the cells are stored at, 30% state of charge. So that's the kind of thing, So uh, that is the, storage, right? Per se, like how it's to be done and how the calendar life, the life depends on that. And for the cycle life, like what happens is, if you operate the cell at a higher temperature, right, you know the aging will be faster again. The rate at which the battery is charged or discharged. If your cell is 1C, 20H, and if you discharge at 40 ampere, right, basically like you're stretching the cell to deliver more. So in such situation, like what will happen is, your cell will be aging faster. And the depth of discharge, right, I'll explain you in one of the subsequent chart graph, that uh, the cells are defined to operate at the optimum, depth of discharge band. So, then, like it has a, better, cell life. So the number of charge discharge
Sorry,
cycle
excuse me, sir.
completed, like
Excuse me, sir.
Sir, you are not
Sir, you're
audible.
not audible.
you cannot hear me
No, sir,
No,
your
sir.
voice is breaking.
now.
Now
Yes,
it's
sir.
Now,
yes, sir, you are audible now.
now is audible. Clear?
Yes, sir. Yes, sir.
Okay. So just hold for a minute. I'll just give me 30 seconds. Is it okay now?
Yes,
Hello?
sir. It's okay now. Yes, sir. You are audible, sir, now.
Okay, great, great. So basically, right, the Wi-Fi signal fluctuates, no? So that's the reason. Okay, and moreover, right, I also got a, very good, cold infection. So the battery, right, so keeps the degrading over time, whether it is just stored or under, charge discharge cycle. So of course, like anything which is existing, it of course it will age, right? At different situation, it will age more, faster or slow. So that's what it means. So it is quite interesting here. If you see the capacity loss, like what you call it, the beginning of life capacity, and with the time, right? So if you leave it at a different temperature, right? So this is how, the experiment has been done on the 28 cell. So if we store the cell at 23 degrees centigrade, right? So over, say 500 days, right? If you store, right? Then the capacity loss will be something like 4% or 5%, max. If we store the cell at 35 degrees centigrade, then after 500 days, right, the capacity loss will be something like 7.5%. And if we store the cell at the elevated temperature at, like 45 degrees centigrade, then after 500 days, right, the capacity loss, like it will be, 16%. So, I'll just tell you, in electric vehicle application, right, we use the capacity fades, right, up to 20%, right? That's it, right? It is not become, it doesn't remain suitable for use in the electric vehicle applications. So the capacity, up to 100 to 80%, like the 20% capacity only, like we use it into the electrical vehicle application. After when it becomes up to 80% capacity retentibility, right, then it is used for stationary applications. Okay. So, like 1.5 year, if the cell is stored alone, right, the battery almost will be having the end of life, like 16%, like it will degrade. So we have to store the battery at, 23 degrees centigrade. So here, uh, uh, what we are trying to see is the effect of the temperature at once we charge discharge at 100% depth of discharge cycle for 20 ampere hour cell. So what happens is, so if you do a charge discharge cycle of the cell at 25 degrees centigrade, daily 12 cycle you are doing without any, relaxations in between after the charge and discharge, then what happens is the cell, right? So, like I told you, like up to 80% we use it. So up to, 5,000, more than 5,000 cycle we can use it if we can maintain the cell temperature at, 25 degrees centigrade. Now if you use the cell at 55 degrees centigrade, then what happens is, 80%, right, 800 cycle itself, like you'll be finishing it at, so that's the kind of thing is. So it is very important, like our topic now here is the thermal management and the temperature, right? So it is very important, to ensure the battery to make operate at the optimum temperature. So you are seeing that, like the cell life is becoming 1/5 if it is operated at 55 degrees centigrade compared to 25 degrees centigrade. Okay. Am I audible now?
Yes, sir. You are audible properly now.
Okay, great. So anytime you have the questions, you can, compile the questions. So at the end of the session, right, I'll be, try to answer as many questions as possible. And here, right, what we are trying to show is, like once you charge discharge, right, if you do a 1C charge discharge, like you're charging at 1C and discharging at 1C, then your capacity retention, right, over the days, right, of usage, right, it is more, right, if you do 5C charge discharge, right. So the C rating also have a capacity fade at different C rating. So C rating also play at a bigger role in the degradation of the battery life. Here the temperature is also maintained. So when we are designing a cell for a applications in the vehicle, right, we have to ensure, we have to make sure that you don't overstress the cell. So try to have the cell in the range of 1C charge discharge. So people will ask for, like, I want a fast discharge, 20-minute charge. The battery should get fully charged in 20 minutes. Meaning you are doing a 3C charge discharge. Of course, then you have to sacrifice the life of the battery, right? So what is more important and critical? Like, we have to think for that line, and we have to do a proper balancing out of it, like what works out the best. Here, the importance of the temperature, like what we are going to show is internal resistance. Like, so if you operate the cell at a higher temperature, right, so at 55 degrees centigrade, right, so your internal resistance will increase, right. If the internal resistance will increase, then of course, like, you'll be emitting more heat. Okay, so we have to ensure you're operating at a controlling the temperature of the cell, ensuring the cell is uniformly maintained at a particular temperature. This is a very, very interesting, so this is what is showing the state of charge from 0 to 100%, say the state of charge, and this plot is showing the direct current impedance. So here, if you see, if the cell is maintained at minus 10 degrees centigrade, if you are maintaining the cell is very, very low, right, then your impedance is increasing. And when the charge is lesser, right, 0 to 10, right, the impedance is more compared to 50 to 80 degree, 80% SOC, right. Here 50 to 80% SOC, right, the impedance is quite flat, is constant. Again, when the charge is high, the battery is full and 100%, right, then the impedance is suddenly increasing, right, from 90 to 100%, right. So that is how is the trend at all the different temperatures. But here, if you see, if you are able to maintain the temperature to something like, say, the blue one, right, 30 degrees centigrade, right, so it is quite flat. But on the other hand side here, right, the lower end of the SOC, right, so it is increasing, but it is far more lesser than the minus 10 degrees centigrade. So this is also is an internal resistance uh, uh, to maintain low during the operation of the battery pack, to have a lesser heat emitted is also important. So what we have seen, right, in all the slides and before, right, so the temperature affects the batteries in 5 major ways. Operations of the electrochemistry in the system, so it affects that. Charge and discharging rate, it affects power and efficiency, safety and reliability, life, and the life cycle cost. So basically, like, we have to maintain the battery to optimum cell temperature, which is something like 24 degrees centigrade. Okay, so on the right hand side, if you see, right, the power limit during the discharge, so 15 to 35 degrees centigrade, discharging operating temperature range. So it works out fine. So we have to ensure the battery cell is maintained within 15 to 35 degrees centigrade, and if we operate more, then the degradation will be faster. And if we use a lesser temperature, 15 to 0 degree, towards then the sluggish electrochemistry, right? What will happen is the ionic movement, right? It will be sluggish and like will not be able to get any power from the battery, like will get very lesser power. So below 15 degrees centigrade temperature, like it will affect the performance and damage due to the charging of too fast, like. And above 35 degrees centigrade, the safety, life, and non-uniform aging due to the thermal gradients will happen. So we have to ensure the safe operating temperature of minus 15 degrees centigrade to 35 degrees centigrade. Okay. So lithium-ion batteries are extremely sensitive to the low and high temperatures. So we have to provide air conditioning system for them. Okay. So here, whatever we have discussed, right? So whatever is the ideal working temperature range. So the life cycles, actual life, will depend on the cell chemistry and the percentage of time spent at the upper and the lower temperature limit, right? So we have to find that what is that ideal temperature range. So if you see the graph on the right hand side, right, the capacity, right, the cell capacity with the temperature, like it increases, and the battery life with the temperature, it decreases. So where it balances out is at 25 degrees centigrade. So in all our application and operation, right, we have to ensure a proper cooling systems, like what we call is a battery thermal management systems, to ensure the battery is maintained at 25 degrees centigrade during this operation. Okay. So like heat generation process, right? So you have seen, right, when you are using your mobile phone, right, when it's charging, when it is charging, right, it is getting heated up, right? Especially, right, you have must have noticed in the Nokia olden days phones, like these days, like the battery BMS is much better up, like so. But still, right, you notice the heat when you are like charging, and when you're talking on the phone, right, you are noticing that your phone is getting heated up. Okay. So it is all because of the movement of the lithium ion, so that is the thing is. So we'll discuss like what are the different heat generation process in the battery pack. So heat generation process, right, there's three categories, like is a reversible process, and reversible process and irreversible processes, and another category is the entropy heat changes, and the process is electrochemical reactions, like which happens inside the battery pack. In irreversible processes, like basically like active polarization process happens, like which is the charge transfer resistance, and ohmic heating process, which is transport in resistance in the phases, and heating due to the mixing, like which is inhomogeneous ion distributions, and enthalpy change, which is the diffusions of lithium ions. So the key component in the batteries, like is a core combination of electrodes, electrolytes, and the separator and the current collectors. So this is the core components, and the terminals and the bus bar, which is outside of the battery, like positive and the negative terminals, and the bus bar interconnecting the cells. So heat, yeah, you can hear.
Yes, sir.
Yeah. So heat generation in the core, in the material, right, is the ohmic heat, like which is the Joule's heat, which is nothing but is the I square R, like the resistance, right? So now, what are the resistance inside the cell? Like we have a resistance at the anode, like here we have the resistance at the electrolyte and the separator, and the resistance in the cathode. So all these three resistances, right, which will add up, so we'll get so this I square R losses, and this is the maximum irreversible heat generated. So the thing is, one of the critical aspect in the battery cell design, but it to reduce the internal resistance as much as possible, and the reversible heat, which is entropic change, so is nothing but IT du by dt. So this is moderate at 1% at a high C rate and to 36% of the low C rate. So here is basically the reversible heat, like which will be for the charging and discharging, right? It will be reversing. So heat of mixing is inhomogeneous ion distributions, and its contribution is very, very little. And heat of enthalpy and phase change, diffusion of lithium ions, its generation is negligible. And heat due to the polarization process, resistance of electrolyte interfacing. So this effect of this heat generation is also negligible. So main, like which is heating, is the ohmic heat and a bit of the reversible heat. And in the terminal, right, it is mainly the joule heating, which is nothing but is I square R in the bus bar. So this is the outside, in the battery pack, like the conductor heats. So here, like, is how much heat we have to remove, like MCP, delta T by dt. So here, whatever the heat generated, and this heat is retained within. So what will happen is, because whatever the heat generated in the battery pack, some heat by means of convections, radiations, and conduction, like it will move out, and we have to like remove this heat generated, which is nothing but is irreversible heat and the entropic heat. So this is what is the method of heat rejections and additions, like so we have we can remove heat by convections and radiations and by the conduction. So we have to remove heat by this, or we have to add heat. Add heat, the situation becomes when is kind of we have to use the battery pack in the extremely cold condition. So this is what is T ambient and T surface temperature on the battery. So that's how like is. So it is all like like these days in ANSYS, right, in the battery model, right, we can build up the battery thermal model for optimize for generate how much heat is generated in the cell and how much heats to removed. So lithium-ion battery failure and voltage effects. So what happened is over voltage and overcharging. So here, right, if you do the over voltage and overcharging, right, then what happens is the lithium plating, like here the cell is designed to operate at a particular cell voltage, like so 2.6 to 4.2 volt. Okay, so if we do a charging, overcharging, then the lithium plating happens, and it will also have the overheating. And if we operate the cell, like to under voltage and over discharge, right, what will happen is like anode breakdown will happen and the cathode breakdown will happen. So basically the battery cell will deteriorate and decompose, kind of thing, so that kind of thing happens, so which will lead to a short circuit and fire, possible fire inside the battery pack. So we're not supposed to operate the battery cell to a value like designed to a lesser value than the recommended value specified by the manufacturer of the cell. So this is what is the lithium ion cell operating window, like the temperature as well as for the cell voltage. Now for the temperature, right, if we operate the cell at a lower temperature, then what will happen is the capacity will deteriorate, and lithium ion plating during the discharging will happen. So eventually that will make lesser lithium ion available, and the capacity will degrade faster. And for a high temperature uses, right, the capacity of course increases, but irreversible chemical reactions will happen, and unwanted, and so this will more instantaneous power like one can get. So like a safe operating window for the temperature is also defined. So you have to operate the lithium ion battery within the safe window of the temperature. Thus, the battery must be kept with a limited operating temperature range so that both the charge capacity and the cycle life can be optimized. A practical battery thermal management systems may therefore need for both heating and cooling system to keep it within the battery manufacturer specified working limit. So here, like lithium-ion battery failure, the thermal runaway, how it happens is like external abusive conditions. Like if you hit the battery cell, by external means, right? Then like you can run away into a thermal, thermal runaway can happen. And overcharging, if you do overcharging and over discharging, the thermal runaway can happen. And high current charging, nail penetrations, crush, external short, all this mechanical abuse if you do, right, like the one you are saying in the somebody is trying to puncture through the mobile phone battery through a knife. So this is the kind of thing it can happen. So what it can go wrong is lithium plating and internal short circuit can happen. Then electrode and electrolyte reactions, like it can react, decompositions can happen, causing like then electrochemical reactions. So once you have the thermal runaway, right, as you are seeing, like what will happen is like leak, smoke, gas venting, rapid disassembly, flames, explosions, like anything, it can happen. So thermal runaway is nothing but is a self-heating chain reactions in a battery cell that causes its destructions while propagating to the adjacent cell. So that is the thing is the electrolyte, right? I told you in the cell, right, is nothing but is a kind of organic solution, right? So because the organic solution, it will easily burn, right? So that's the kind of thing it happens. So what happened is like when breakdown of the SCAI layer happens, like something at around 40 degrees centigrade, at around 100 degrees centigrade, the pressure and temperature increases, and releasing of flammable gases and exothermic breakdown of the electrolyte happens. But still, at around 100 degrees centigrade, the no flame fires are seen yet. At 200, around 180 degrees centigrade, right, the separator will melt. Separator is nothing but is a kind of polyethylene or polypropylene. So, and then possible venting will happen. So when it is roughly 250 to 280 degrees centigrade, cathode active material breakdown happen, oxygen releases, and ignition happens, and eventually like we get to see the thermal runaway. So there are various method of cooling the battery pack systems. So like on the left hand side you are seeing the cylindrical cell, and on the cylindrical cell, like it is putting into a kind of enclosures on which cooling fan is blowing air. So basically these days in the two-wheeler, right, and the battery pack. So this is the kind of thing you will get to see. So in the pouch cell, what happened is, we use, like the green color you're seeing here is a kind of, heat transfer plate, which removes the heat from the body of the cell through this, and it brings the heat out to these fins. And on the fins, right, we put a cooling plate, cooling jacket. So the heat is removed from there. And on the prismatic cell, like which is made, the height should be very low, so otherwise there will be a temperature gradient across the height. And what we do is the cells are placed onto a on a cooling plate, so on which we have a coolant inlet and coolant outlet. So battery cooling methods, like we have a air cooling, convection to air, either passive or forced or active cooling method. And the liquid cooling is cooling by circulating of water-based coolant through cooling passages. Like in the plate, right, we have we create the cooling plate, right, we create the water coolant passages. The coolant is mostly nothing but water glycol as of today, so that is been used as a 50%, like what is used in the engine coolant system, right, the very same thing which is used. And refrigeration cooling, like, is a cooling by circulating of refrigerant through cooling passages plate within the battery structures. Also, people are trying the immersion cooling, meaning is the battery pack, battery cell is immersed into a in a liquid, so which is nothing but is cooling by flooding the battery with the dielectric oil, or which is then pumped out to heat exchange the system, which is quite inconvenient, right? A long time back, 10 years back, people tried that, but still it is in the lab stage. Then the cells are immersed in a non-conductive fluid, like 3M has come out with this engineering fluid with a high boiling point. And cooling by using phase change material is also quite common, like probably in some two-wheeler industries, like they use this for their cylindrical cells and for phase changing material coolant. So in phase changing material, what happens is the phase change material absorbs the heat energy by changing state from solid to liquid. While changing phase, the material can absorb large amount of heat with a little change in temperature. So that's the kind of it is solid, then it is melting, and it's become liquid. So here, right, it is absorbing the heat from the cell. In the refrigerant and coolant, right, the refrigerant sometimes directly flown across the cooling plate, or we use the refrigerant to cool the coolant, and that chilled coolant is flown into the cooling plate, into the battery pack. So passive cooling by using air from outside, right? The outside air is flown onto the battery, right, which is I told you already, in the two-wheeler industries, like it will be quite popular. And active cooling, like by using cabin air, basically prior and inside, right, what is done is kind of chilled air from the cabin, right, is flown through above the battery pack. So basically in the vehicle we have air conditioning system, so we have this facility to get the chilled air which is flown onto the battery pack. And independent air heating cooling systems IMIV first charge, right? This vehicle have this implemented. So there is a separate cooling system and heating systems for the battery pack itself, and which is by means of the air. So passive cooling. Okay. So primary circuit with the chiller and the heat sink battery. So here what happened is, this is the battery, like it has a heat sink and it has a heating coil, like like with electricity you can heat up the coolant in kind of cold temperature. And for cooling, mainly like there's a water pump here, so it keeps circulating the coolant in this. And there is a like chiller here. So the chiller from the condenser, right? Sorry, the evaporator, right? The how to say, the refrigerant, right? It flows through the chiller and keeps circulating here, and it keep cooling in the condenser. So that's how is and secondary circuit with the chiller and heatsink is very similar, like what is used normally in almost all the vehicles. And here thermal management systems and liquid cooling systems. So we need to know the pros and cons, like in air cooling systems. I know both the cooling and the heating is feasible, and it removes very little amount of heat. So that's what is very is a negative point for this. And separate cooling loop are not required, like for air cooling, and it needs a very high blower power for blowing the heat, blowing the air onto the battery cell. All waste heat eventually has to go to the air, so we are not handling any liquid per se, so we can discharge the air into the atmosphere. So that is a positive point for the air cooling systems. But more temperature variation in the pack. So basically, air, we really cannot control the temperature variations in the pack, right? The delta temperature from the one cell to the extreme cell, right? It will be very high. So low mass of the air and distribution in the systems. And the cons, like negative point is connected to the cabin temperature control. So what happens is, whatever the cabin cooling capacity is used, part of it for the cooling the battery pack. So no leakage concern, basically, like the air, if it gets leaked into the atmosphere, nothing happens. And the air, right, if it gets leaked into the battery pack also, there's no problem. So basically, like for air cooling, no leakage systems, but potential venting of the battery gas into the cabin. So what happens if you are circulating the cabin air? So whatever the air which is used after cooling the battery pack, right, it should be left into the atmosphere. We cannot bring that air from the battery after cooling into the cabin again. So in this case, what is happening is, we are chilled air, we are just leaving it into the atmosphere from the cabin. So that increases the load into the compressor in the cabin cooling systems. So no electrical short due to the fluid concern, and lower cost for the air cooling systems, and lower development efforts required, easier to maintenance, like there's nothing much of the components. And the negative points again for the air cooling is potential of venting of the battery gas, that's already we discussed, and temperature difference between air and the cell can be more than 25 degrees, like which is not really very expected thing. But wherever, right, we don't have any option of any chill liquid. So we have to go for a air cooling. Basically, something is better than nothing. So that's what is the concept is. So liquid cooling is like positive point is pack temperature is more uniform, thermally stable. It has a very good heat transfer capacity and better thermal control. Right, the cell temperatures can be uniformly controlled, across the battery pack, and lower volume. Like it can be very compact design, and we can do a cooling and heating, easily, adaptable. And the negative points for the liquid cooling system is additional components, increases weight, liquid conductivity, like electrical isolation, like we need to ensure leakage potential, like we cannot have the coolant leaked into the battery pack, so which will cause another problem of high voltage insulation failure, and higher maintenance cost because of the more components, and higher viscosity at cold temperatures. Basically, the coolant will become dense with the temperature falling, and give rise to the higher viscosity, and is basically the system is expensive. So why BTM is needed? So battery thermal management system is needed to operate the battery pack in the desired temperature range for optimum performance. Is 15 degree to 35 degrees centigrade. That's what we have seen in our earlier presentation. So reduce uneven temperature distributions in the cell. Uh, Basically, like if one of the cell in the battery pack goes bad, right? So the battery pack is not usable. Like we have to replace that cell. So replacing any single cell is not really possible. Like we have to replace the complete battery module. So that's the kind of thing is. So we really don't want to have any cell spoiled over the life of the battery pack, which is something like 8 years or 9 years. So reduce uneven temperature distribution in the cell, less than 3 degrees centigrade to 4 degrees centigrade, and less than 10 degrees centigrade for the long prismatic cells. So basically the prismatic cells are constructed with a lesser height, and reduce uneven temperature distribution across the battery pack, less than 4 to 5 degrees centigrade, and prevent the battery from going above or below the acceptable operating temperature limit. Maximize useful energy from cell and pack, eliminate the potential hazards related to uncontrolled temperatures, thermal runaway, and to use a small amount of energy for operations, right? So for operating the battery, thermal management systems, we need to use as little energy as possible. So battery management system should be simple, compact, and lightweight. It should be modular, scalable, easily packageable, energy efficient, have low cost for manufacturing and maintenance. It have easy access for maintenance, and it should allow the pack to operate under a wide range of climatic conditions, provide ventilation if the battery generates potential hazardous gas, and design for fast charging. It should be reliable, optimum temperature range it should operate in, and the small temperature variations. Like we really don't want a temperature. The ideally, like the inlet and outlet temperature of the coolant in the battery pack, should be maintained to 2 degrees. So what information we'll need, for designing a better efficient battery thermal management systems? The cell shape plus the model geometrical configurations, prismatic, pouch, or cylindrical, like acceptable temperature range, acceptable temperature difference, maximum and minimum temperature limit, thermophysical properties, the battery heat generation rates, heat rejection rates from the battery, prismatic power, and needed to push for fluid coolant through BTMS. What is the parasitic power? It will be consuming. The weight of constants and battery locations, and the cooling media available on the vehicle. So these are all different materials like which are used for thermal management inside the battery pack. So in between the cell, like there's a compression tolerance pad, accumulated expansion and concentration of the cell, then thermal runaway preventions, so it will prevent. And thermal interface material like promotes the heat flow, like here. So there's a cooling plate and there's a thermal interface material which ensures the proper gap filling and contact with the cell. And the seal pack, the seal pack covers for temperature, air, dust, and water tightness. The sealing, fire blocking polyurethane foam minimizes the durations of the fire by fire suppression. So on the top, right? So the fire should not come into the cabin. Okay, so I'm just in time, so I'll thank you for bearing me for so long. So if you have any questions from any of the segments, like I have some time now, we can discuss.
So participants, are there any questions? Am I audible?
Yeah, I can hear you.
So participants, are there any questions?
Participants can put the questions in chat box also.